Okay, welcome everybody to the 240th Earth to Class program. And we are continuing to have this next year. At least that's the plan. We're privileged and pleased today to join once again with our friend Dallas Abbott. As I put in the Earth to Class website for this presentation, Dallas has been studying impact craters and the history of the Hudson River for many years. And she's been probably with us for presentations more often than anyone else at Lamont. So we're very pleased that she continues to join us. And welcome everybody. Dallas, there's a lot of old friends here.
Yeah, I see. That's great. Yeah. So now I got to share the screen. Okay. So what I've been doing is I've been working on evidence, physical evidence of multiple large impacts into the ocean. And what I'm trying to do is to come up with some new strategies because oceanic impact craters are really hard to find, partly because when they form, they erode their walls with the wave, the tsunami wave that they create. The really large ones should have central uplifts, but there's a problem of distinguishing them from seamounts. So what I found out is that there's a really big impact crater in the Arafura Sea, and we found submarine spheral aggregates from this thing. And I think they were carried either atmospherically, probably by a tsunami, several hundred kilometers until they landed in the Gulf of Carpentaria. And also impact craters, big ones at least, they're going to excavate down to the basement. So there should be basaltic fragments in sediments in places where the sediments are otherwise thick. And also the biggest impact craters will be, you can use satellite altimetry to find them. And also, for the more recent ones, mega tsunami deposits and oral traditions may also help, but you definitely need geophysics and marine geology. So the first one I'm going to talk about is, this is the Arafura Sea crater candidate, and here's the Gulf of Carpentaria, and I'll show you where there were cores here, and for a long time, because there wasn't much data, there were these two round holes here that we thought were the source of the material in the cores here, but in fact, those turned out to be artifacts, and they don't show up in more recent data. However, there is a crater candidate. So here's the crater candidate in the Arafura Sea. You can see this is a gravity gradient map, this thing, and you can see that there's this kind of small dark hole. But that's actually a big crater. It's like 40 kilometers in diameter. And you can see it partly because it's so big and also because the water is shallow. The satellite altimetry works best in shallow water, and also in shallow water, it's harder for the tsunami to erode the crater walls. And then these are cores where we found these spheral aggregates. We found impact spherals in all of these. And in some of these, we found a native iron, which is something that you wouldn't normally expect to find on the seafloor. So how do you get spheral aggregates? Well, first, here's some modeling of the gravity gradient data. And Walter H.F. Smith, who's the guy he and Dave Sanwell did the gradient data. So here's the crater, and it has a central uplift because it's big. And you can see that this thing is on the order of 25 to 25. It's on the order of 40 kilometers in diameter. So here's the data. The blue is the satellite altimetry data, and the red is the model. So he did a model of first he did a model of the vertical gravity gradient and the gravity in milligauss. So here's an east to west profile, and here's a south to north profile. And you can see, I mean, the gravity gradient data is really what he has the most confidence in, because there's no ship tracks over this. So and he got gravity data from satellites. And what you can see is that, particularly for the gravity gradient data, it fits pretty well. And also here's a model of what the crater looks like. I think it would have a central uplift. In his model, he's just got a kind of area of dense material, but a crater that's 40 kilometers across would invariably have a central uplift. So I think he's kind of introducing that in there by putting in, this is a denser area. And he's also got a thing where he's suggesting we're ejected to the northwest. We don't know. So here's what happens during oceanic impacts. This is a picture of just a lightning storm. But what happens during an oceanic impact is you get all kinds of water vapor and rocks and sediment that are thrown up into the atmosphere. And based on what we know about large submarine volcanic eruptions, like in the eruption of Hunga Tonga in 2022, they basically got more water vapor in the stratosphere from that event than they'd ever seen before. It went up 60 kilometers. And for perspective, the plume from a regular volcanic eruption, which doesn't have nearly as much water, that like Pinatubo in 1991, it went up 35 kilometers. So this went up almost twice as high. And if you had a large impact into the ocean, you'd do the same thing. All the heat would vaporize tons of seawater. And then you would get, and what happens then is when you get all that water so high, you get huge amounts of stratospheric lightning. In fact, the Hunga Tonga eruption, it not only produced the most stratospheric lightning they had ever seen, at some times it was the most stratospheric lightning on the entire planet. So it's a huge amount of lightning. And then what this lightning does is it actually fries the rock and the sediment, and it makes because if there's any iron in the rock at all, what it does, or it makes spherules. And the ones from submarine eruptions aren't that large. The maximum size is about 80 micrometers, but the ones from impacts are much larger. So that's why we're pretty sure that these ones in the Gulf of Carpentaria are from an impact and not from a large volcanic eruption. Also because the Gulf of Carpentaria is much closer to the prospective impact crater than it is to any volcano. So here's what these things look like. So you get, these are the spherules. So these are mostly iron oxide. And that's what you get in the submarine ones. In the ones where you fry volcanic ash, you get about half silicate spherules and about half iron oxide spherules. But here it's basically all iron oxide spherules. And then because everything's so hot, the lightning makes these iron oxide spherules, and then in between you've just got sediment that's been prematurely lithified, because this is from 2 to 3 centimeters depth in the core. And I can tell you that normally at that depth in a marine core, everything is just mud. There's no rocks except for rocks that were brought in. So these are rocks that were brought in. So I'll show you this, and I'll show you what it looks like in thin section. This is the same rock in thin section, and this is the largest spherule we found. So basically, the largest spherules are way larger than you'd ever get from a volcanic eruption. And you can see in the thin section, these spherules, sometimes the centers are hollow, and most of them are perfectly round. They're these absolute perfect spheres. So this is a spheral aggregate. And here's the big one that I talked about, which is the biggest spherule that we found. And then here's the spheral aggregate. And there are several things to know. One is these are element maps. Notice that this thing does contain some nickel. That's important because, if it's an extraterrestrial body, even if it's a comet, it would have had some nickel. And then here are these iron oxide spherules, so that's iron and silicon. And here's the aluminum map. And the thing about the aluminum map that's important is that just about everything that has silicon also has aluminum. That means there's no quartz, or essentially no quartz. And that's important because if you wanted to look for one of the primary indicators of impact is shock quartz. And I think eventually we'll find it, but most of the silicate, most of the minerals in this stuff are not quartz. So it's been pretty difficult. So here's the largest spheral aggregate sizes versus distance. So here's the mean water depth. You can see it's pretty shallow. 50 meters is like nothing in the ocean. And then these are the largest ejecta fragments in the cores. And for some reason, they're smaller as you get towards the crater candidate. I think part of that, the water's a little shallower here, so that makes it a little harder to transport it. But I also think if it's being transported by a tsunami, and there's some the way the cores are set up, it looks like there might be a little bit of an erosion unconformity, then what's going to happen is the stuff is going to move in the tsunami until it gets to a point where it can't move anymore. And so that means that the area closest to the crater isn't actually going to have the largest particles. So, and you can see that this even contains some oolites, which is interesting because the crater candidate's on a continental margin, and things like oolites only form in shallow water. So it suggests that wherever these things came from, it was pretty shallow water. And here you can see some more of these spherules. And then these are tiny, tiny, tiny spherules here around the rim of this hole. So, and this is native iron. So all of these have spherules in them, but you can't see them all in this picture. Okay, so here are the layer counts. Now, the way that we've found this layer, has iron oxide spherules in it, and the sediments are mostly carbonate, which has basically a zero magnetic susceptibility. So what we did was we measured magnetic susceptibility, that's the pink, and here's the ejecta layer thickness for a 34-kilometer crater. And then also we counted spherules. And what you can see is that outside of this layer thickness, there's basically no spherules. I think one, that could be cosmic down here. So this is the layer thickness, and here, this is the layer thickness, and here's the expected thickness of the ejecta layer from a 34-kilometer crater. So it fits. It's about the right thickness. So then we'll just move now to the Indian Ocean. Let me go back. So I've talked about these before. In southwestern Australia, there's early Holocene tsunami deposits, and there's no obvious seismic source. There's basically no beach in these areas. And they go up to 151 meters above sea level. And these are chevrons, they're V-shaped, so they point backwards toward their source. So their source, oh yeah, here's one that's at 192. So they go very high above sea level. Like a typical tsunami deposit would only go like maybe 30 meters above sea level. It's really hard to get a tsunami deposit that goes this high above sea level. So where is the source? This was the paper that reported on those chevrons, and this was what they thought was either a potential area of a meteorite impact or a slide. However, I think what this is defining is basically what they're getting is the latitude, rough latitude of the source. And they're not real, they really have no constraint on the longitude. So the source could be here, the source could be here. Okay, so here's what we found near on the other side of the ocean. So here's Australia, here we are in Madagascar, and this core at 25 south, they report spheral aggregates, and they're definitely not cosmic spherals. This core we found melted nickel. And as I'll show you, there's a mega tsunami event here that was at about 11 to 13 Ka, the Younger Dryas. And these are also cores with basalt fragments in them. If they're right on the ridge, they could be something else. Here, this looks interesting because there's a whole bunch of them. So if I was going to look for more spheral aggregates, I would start with these other cores that have basalt in them, especially something like this where you're off ridge. And remember from the Gulf of Carpentaria, like if there's a source crater for this, it could be, here's 300 kilometers. It could be anywhere around here. We don't really know, because we also don't know how far a tsunami would travel. So, so if there's a source crater out here, it's not visible in this stuff. I've asked Walter Smith, I sent him this presentation and I've asked him to look to see if he can find anything. I don't know. Deep water craters are pretty hard to find. But if we can find more spheral aggregates in this area, that'll suggest that something's going on. And then you might be able to go out and do geophysical work and try to find a source crater. So, but cores with basalt are not very common. There's maybe less than 10% of all the cores ever taken at Lamont did they find anything like that. Okay, so here are the spherical aggregates from the Southwest Indian Ocean. And they're basically made of magnetite plus wüstite. And the wüstite tells you that, that it was a very reducing event that produced them, something like the lightning and an impact. And also they have low nickel, so they're not cosmic spherals. And also these are very clearly spheral aggregates, like I showed you. And as far as I know, these are unconsolidated sediments. And as far as I know, if there's no volcano nearby, the only ways you can get these things is with an impact. So these are very definitely spheral aggregates. Some of the other ones that I found, they weren't so interested in whether or not they were. And also, some of our spheral aggregates have fossils incorporated into them. And this one, you can see, this is a marine microfossil. So, and so is this. So, because under the conditions of an impact, you'd be throwing up lots of mud from the ocean bottom. And then with the lightning, you would make things like these metallic spherals. But then because the temperatures are so high, it's going to all get glued together in a rock. And that's exactly what you're seeing here. Okay, here's what we found in also in the Southwest Indian Ocean and in young sediments. And this is melted nickel. And basically, to melt nickel, the temperatures have to be greater than 1,500 degrees centigrade, which is higher than you'd ever get in a volcanic eruption. So these have to somehow be related to an extraterrestrial event. Okay, so here are the chevrons in Madagascar, which we went to visit. So when Google Earth came out, we found these things. And the run-up, which is that the distance that the tsunami wave went above sea level, is 63 meters. And this thing is 46 kilometers long. I mean, these are the most spectacular tsunami deposits on the planet, basically. I've looked at some of the others, and you get things that are windblown, but these have marine microfossils in them. So they're not just windblown. And actually, we've looked at them in a lot of detail. These are both in thin section. You can see them better. And what you can see is the marine microfossils, they tend to be just pitted on one side. And the reason why is they're too big for the wind to move. And so they just sit there on the sand dune, and they get pitted by the sand grains moving by. It's, you probably, if you've ever seen sand move in the wind, there's a process called saltation, where the grains just skip along. And if there's anything sitting on the surface of the ground, it gets hit. And if it's at all fragile, it gets pitted. So that's what's happened with these guys. So here is the Fenambusi chevron. And this one is 45 kilometers long. And the thing that we noticed about this, see this line here? This is a fault scarp that's 175 meters high. So and this is all tsunami material coming in, and it actually went over the top of the fault scarp, which is amazing. So this thing is 45 kilometers long. So you have to have had a really big tsunami wave. The wave height to get this kind of run up would be on the order of, it's about 1/3 the run up. So you can see that it would be on the order of 90 meters high or so, 70, 80. So here is a picture of that escarpment when we went in the field. So we were staying down here by the beach. And so the tsunami went up that cliff, which is pretty amazing. So just think of a tsunami that could come in and go up a cliff that high. And here are marine microfossils from the sand, 2 of many. They've been pitted because, they're in sand and the sand is moving around. And also this event happened a while ago. It happened like 12 or 13,000 years ago. And what's interesting also is these are mostly benthic foraminifera. They're not pelagic. So again, to get those guys, you have to be eroding stuff from near the bottom of the ocean. So here was where we're going up. This is what it looked like when we were going up. There was only one road up the escarpment, and we would take our field vehicle up it every day. And the local people mostly didn't have cars. They had these zebu cattle. And so they're stopped because their goats are underneath, and they have to get the goats back. So we kind of waited for them to, get done with their business. And here's what it looked like going down the escarpment. This was the only road. This was actually one of the better roads in Madagascar. And, almost everybody walked. If they didn't use their cattle, zebu cattle, they just walked. So here's what it looks like. So here's that satellite view again. And I'm going to show you pictures from here where we took every day we would go up the road, which was down here, and then we would go along the top of the escarpment. And then we went up here where there was a village so that we could talk to people and they could guide us. So here we are at the top of the escarpment with our guides. So this is looking out to the ocean. Just to give you an idea, this is very near to give you an idea of just how far away the ocean was. So we're standing on sand that was deposited by the tsunami, and we're looking out to the ocean. So we were like 7 kilometers away from the ocean, a long ways. And here's Hubi, who is one of our field assistants, was a graduate student. She's now a professor in Madagascar. And Hubi is her name. And she's a seismologist. So we had 2 Malagasy grad students with us. And we needed them because to get around in the field, everybody spoke Malagasy and then, or French. And of course, we spoke English. So we had to have field guides who were trilingual, and they fit the bill. So when we think this happened, the Younger Dryas was about 12,849. And our dates of the Madagascar chevrons are 12,900 plus or minus 67. And there also was another interesting event at Abu Hurayya in Syria. And there's also the postulated Younger Dryas event in North America. So there's an ice core platinum anomaly. And there's also a bunch of, people have found a whole bunch of deposits in North America. So I think there was probably one big event at this time, a comet that came in and it splintered into multiple fragments. Okay, so here's Bruce Mass's summary of oral histories. So, I mean, basically, if you've got an oral history, it's something that probably happened within the last 40,000 years. And his stuff, I mean, it was definitely centered in the Indian Ocean. And this was where I had originally postulated a crater down here. We haven't really been able to verify it. However, finding these spheral aggregates in the Indian Ocean suggests that yes, there is a crater there, but we haven't actually found where it is. We think it's about this latitude though, because that at this latitude, that would produce the chevrons that you see in Madagascar that I just showed you, and it would also produce very big tsunami run-ups in Australia. Now, so what about what's going? So here are the locations with hot water from the sky. And what I find interesting about that is this is right on top of the crater candidate that I showed you for the Gulf of Carpentaria. So it's not exactly at the same location, because if you were too close to the crater, you'd get killed. But I think it's interesting that there's oral traditions from Irian Jaya where they talk about hot water coming from the sky. Or actually, this is hot water from the ocean. So both of these, and then also there's something down in Tierra del Fuego. And I'll show you something that we found, although it's not the right age. And up here, we've got hot water from the sky. If it's right on the ocean, it probably was a crater in the ocean. But we don't have spheral aggregates for all of these. I've just been looking through the literature and trying to find stuff. But I think there was definitely a very big event in the Indian Ocean. Okay, so this is the description from Indian myths. They describe them as doomsday clouds that looked like a herd of elephants, and they filled up the sky. And they also they have the deluge myth, and they basically describe fiery particles, fire falling from the sky at the beginning of the deluge. So I mean, if you're going to get a deluge from an oceanic impact, you would definitely see first the ballistic ejecta from the impact would be very hot, and then you would see the deluge, because of course the temperature of the impact is 15,000 degrees centigrade. So you get water going up into the stratosphere, and then it takes a while to cool down to the point where you get rain. So definitely you should see fiery particles first, and that's exactly what you see. Okay, so now we're getting back to New York, where I've talked to you before about what's going on in the Hudson, where we have stuff that's pretty definitely extraterrestrial, and we still haven't found a source crater, although I think there's evidence for a sediment slide in Carteret Canyon, which is so young that the sediment, basically, there's no sediment cover on it. So it's geologically very recent. So within the last, 3,000, 4,000 years. So something happening in or near Carteret Canyon. And then I'll show you some of the data from CDO 213, some of which you've seen and some of which you haven't. And then also there are rock fragments. I think you tend to get rock fragments on continental margins. So here, this is actually part of the extent of the Hudson Canyon. The Hudson Canyon goes across the shelf here, and this is the Hudson River. But I'll also call your attention to this bay, because this bay is directly across. So first, tin-covered forams. This is what we found in the Hudson River, and tin is not a normal composite. These are, first of all, too old to be modern. They're like 11,000 BC. And this is the first time anybody ever found these things. So here's a picture of a foraminifera. This is what they look like. The normal foraminifera that we find in the Hudson are kind of white, and these were this very strange yellowish color. So then we put them on the SEM, and we found that the foraminifera were coated in tin. And here's a thin section of the same 4M, and what you can see, we've had trouble getting more of these things. The tin coating is very fragile. It's starting to peel off in the thin section. So the tin, because this is an image in backscatter mode, and tin has a very high molecular weight, the tin is bright. And we were able to get these when the cores were still wet, so that we were able to sieve them more easily. So here's pictures of the tin from from the forum that I just showed you. And you can see that tin, actually, if you have enough of it, it has 5 peaks, 5 extra. This is the EDS. And also the tin, we found this in the ice core too. We found tin in cosmic dust in an ice core, and it modeled better if you added in iodine and xenon. And notice also this particular sample has nitrogen in it. Now, this is really weird because xenon and nitrogen are typically gases, and also in Hudson River sediments, you don't normally see nitrogen at all because it's a bio-limiting element. It gets scarfed up. So this is the first time we ever found nitrogen in anything that we looked at. And what we think in the ice core, we made the argument that the xenon is actually produced from iodine by bombardment with cosmic rays. So we think that the tin that's covering those 4Ms comes from cosmic dust. And the nitrogen, I think nitrogen can have various forms. I think the nitrogen is in a form that's not biologically active. Otherwise, I don't see how it could have survived. So these are 5 analyses of the same thing. And also, we did find nickel. So, I mean, nickel is not commonly found in terrestrial stuff. And so this is cosmic dust, without a doubt, or the tin and the nickel certainly came from, and the xenon and the iodine, and probably the nitrogen, they all came from cosmic dust. Okay, so here's another form, tin-coated form. This is what it looks like in visible light. This is what it looks like in backscatter mode on the SEM. And here's the analyses of it. And notice, again, here it's a small nitrogen peak, separate analyses. Here, this is another analysis of the same one, very definite nickel peak. So this is extraterrestrial tin. And in the same, a few centimeters lower in the same layer, we actually found stuff that's quite high in nickel. Like this is like on the order of, I don't know, 10% nickel. I actually have the data in a table. So, there's very definitely some extraterrestrial. And here's another big surprise. We found neon in these samples. Neon's another noble gas. So where the hell is it coming from? Well, I think these gases have to be coming in on cosmic dust because it's neon again. It's something that nobody ever found before in Hudson River sediment. And here's another piece. I mean, the nickel there's really a lot of nickel here. And also we're seeing a neon peak. So this is some kind of cosmic material that has made it into the Hudson somehow. And in with this cosmic material, there's other evidence that this material came from the open ocean. This is a radiolarian. Here it is in visible light. Here it is in SEM image. Radiolarians don't live in the Hudson. And this site is, way far up the Hudson. So I don't think anybody's ever before found radiolarians in Hudson River sediment. And then we have foraminifera have been found in Hudson River sediment, But the question is, but they can't live in the Hudson because the salinity is so low. So where did they come? They came from the open ocean. And here's some corroborating evidence. This is a coccolith, and coccoliths can't live in the open ocean. So this coccolith was inside the foram, because the foram was actually, that's what it was doing. It was eating the coccoliths, and then they end up inside. So the foram, when it was alive, sucked in the coccolith, and then it was transported into the Hudson. Okay, and then the other thing that we found in these layers were these. See, normally these foraminifera, of course, would be white, like this part here, but they're coated with a dark material, and that's manganese. And the reason why that's important is because all the Hudson River sediments, Lamont routinely logs them. They're black because they're filled with organic matter, and you can't coat stuff with manganese if it's that if the sediments are highly reducing. So this stuff, again, it had to come. So here's the manganese and iron peak. So these are analyses of these foraminifera, and what you can see here, it's just manganese, but in here it's just manganese. But here you've got a little bit of iron, but you still have some manganese. So these foraminifera were transported into the Hudson. They absolutely, and they sat around for a while on the ocean bottom before they were transported too. They didn't just, they must have been buried in the sediment and then moved. So what happened? Here's the stuff I've showed you from CDO213. So you can see, first of all, it's pretty far from the mouth of the Hudson. It's up there. It's actually up nearby Lamont. Here are some dark cores containing dark rock fragments. This is the Hudson Canyon. So these might be worth looking at. I mean, we get some rock fragments in the Hudson. It's stuff eroded off the Palisades Sill. This, I don't know. I have to see. What does it look like? Does it look like it came from the Palisades Sill, or does it look like it came from basement outcrops? And then here's this bay that I'm going to show you more about. So here's the Mississippi Delta, and it flows from space. And so here's the delta, and notice they call it a bird's foot delta because it looks, it does look kind of like a chicken foot. And notice that the claws point towards the ocean. So the river is flowing in this direction, and the claws point towards the ocean. Okay, now we're going to look at this bay, and here's Carteret Canyon, which definitely had a very recent sediment slide. So something happened there. And here's the bay. So I'll show the bay in the next picture. And what's interesting about this bay, see, here's you get longshore drifts, so you get these sand islands. And then you have this, which to me looks like a reverse delta. So what it suggests is that there was some kind of big wave that came in here, and it broke through this island, and this is a lot of sediment, and it transported sediment, and it made a delta, a reverse delta. So the source of this sand is something that came from the ocean, and it's pretty close. It's about the closest point on the shore to Carteret Canyon. So I think the two may be related. So here's a picture of Carteret Canyon, and here's the cliff with a circular head wall. Let's see. So the thing about it is that most submarine canyons have a head wall, but the head wall doesn't look as round as this. So it's possible that this is a small impact crater. We don't really know. But the thing is, these are some of the chutes. See, they have grooves in them, and the lower chute, and there's basically no sediment on top of the grooves. So that tells you that this thing slid geologically extremely recently, and there's actually stuff out on the shelf edge It has a wavy surface and shallow channels, which is which is probably material that slid out of Carteret Canyon. And is it related to the stuff in the Hudson? We don't know, but it's certainly the closest thing. Okay, now we're going to switch to another layer of spheral aggregates. And this was found off of the coast of South Carolina. These are Oligocene spherals. And they're, again, they're very definitely not cosmic spherals because they're iron. They have almost no nickel. And they do have wustite as well. So not cosmic spherals. And the pictures, they showed just individual spherals, but I'm making a guess here that they are spheral aggregates. I'm going to write to the people. So where are these things? The spheral aggregates are in Oligocene sediments off of Sullivan's Island, and there's actually basaltic rock fragments in an Oligocene core here. So this core is the right age to look at to see the source, and actually there's maybe something small crater candidate off of here. I can see something in the bathymetry, but I don't like to say anything until I've actually had a chance to look at the basaltic rock fragments to see what's going on. But the thing about these spheral aggregates is you can get very large spherals for rather small craters. So the source crater doesn't have to be that large. Okay, so here we have some stuff that was found off the coast of Argentina. And again, it's iron oxide. These spherals have these very characteristic quench textures. I know you've seen some of the pictures from some of the ones in the Gulf of Carpentaria. They have the same kind of quench textures. So again, iron oxide, definitely not cosmic spherals, because cosmic spherals, particularly if you make thin sections of them, they'll have olivine in them, and they'll have also sometimes little bits of nickel. So these are not cosmic spherals. Okay, so here, these are Jurassic. And again, you have some stuff on the shelf with basalt in the sediment. Have to look up the cores and see if any of them are Jurassic. There's also a hint that there's something going on here. This is younger. It's not Jurassic. The oral traditions of the Native Americans in Tierra del Fuego do talk about hot water coming from the sky. So there's probably something there. And so here, now we're going to the Arctic Ocean. So these are Arctic Ocean spherals. They're interesting because they don't have any appreciable nickel, but they have iron and they have zinc. And so the author of this paper, Darby, thinks that they come from an area near the Elizabeth Islands because they are they're carbonate sediments, but they contain zinc. So here's the Elizabeth Islands in here, and here these are the Elizabeth Islands. And these things also get ice rafted all over the Arctic Ocean. But from the ages of the sediments where they think that this event happened about 780,000 years ago. So it's old. And again, the spherals, they're up to 100 micrometers in size. So they're too big to be from a volcanic eruption. And there are some volcanoes in Alaska, but they're not very close. So it seems like an impact someplace in this region is the most likely explanation. So I think in conclusion, spheral aggregates are a potential method of locating oceanic impact craters. I'd say that satellite altimetry and detailed bathymetry and geophysics are both required. Clearly, further coring and geophysical work are necessary. And if you have oral traditions of hot water from the sky or the ocean, tsunamis and other floods, these may be helpful for impact events during the last 20,000 years. Okay. So that's my the
Thank
end.
you very much, Dallas. Very interesting.
Yeah, well, I
Um,
recently figured out the Carpinteria stuff. So,
yeah, one question that I have to begin. The cores that you're using, are those from piston coring by Lamont ships or by
well, the Carpinteria stuff was taken by the Marion Dufresne. It's a French core, but it was a little Australian scientist who was chief scientist. But the other cores are Lamont cores.
okay, do you have any of the deep sea drilling project stuff or ODP stuff?
I haven't. I think that would be a good thing to look for, definitely. I think to go through the ocean drilling stuff because they do routinely measure magnetic susceptibility, and these layers should have a very high magnetic susceptibility. So yeah, somebody could go through the ocean drilling. Um, yeah, if anybody wanted to do that, it would be great. Just go through the ocean drilling stuff and see if they could find layers with high magnetic susceptibility that are about the right age. These things don't necessarily show up in core photos because the core photos of the samples that I got from the Gulf of Carpentaria, even though some of these frills are huge, you couldn't see them in the samples. But what you saw was that they had a very high susceptibility. And then once you sieve them, the spheral aggregates showed up. But the spheral aggregates have to be really huge before you would see them in a core photo.
Okay, thank you. Richard, you have questions?
My audio. Yes, you see the lightning discharge in those Icelandic eruptions. Is that common just because there's so much water vapor in the atmosphere?
Yeah, yeah. And also, I mean, you get yeah, you get the Icelandic eruptions. I mean, a lot of the Icelandic volcanoes are sitting on top of glaciers. So when you get an eruption, you get a lot of water vapor.
And
The
is that I'm sorry, go ahead. I'm just wondering, the lightning, it's the charged particles of the water is charged electrostatically. It's giving off the discharge as lightning.
Yeah, well, it's just it's water and the ash itself gets
I
charged
see,
as
I
well.
see, I see.
I mean, if you have a lot of quartz in the ash, quartz is piezoelectric. So if you squeeze it, it generates electricity.
Right, okay.
Other questions? Okay, if not, let me just remind people, this is the last Earth class for this academic year. We will start again in September. Everybody stay healthy over the summer. And I want to thank Dallas again for joining us. It's always a pleasure to hear what you've been doing, Dallas.
Oh, thank you. It's always fun to talk to you guys. You ask good question. And, I always like trying to put it together. At this point, I'm trying to put a lot of things together so that maybe, I mean, at some point I'm going to have to stop doing science, and I'd like to have a body of work where people could kind of take it up and, do some more.
Right. Well, we're going to be editing the recording and we will have it up on the Earth Class website. I'll send you a link for it so you can include it in some of your proposals.
Okay, thanks.
Let people see what you've been doing. Reminder again that NIASTA is going to have a program on the Lamont campus in early August. So I hope some of you will be able to join us for that. You can go to the NIASTA website to get more information. And it's not as beautiful a day as it was last few days, but it's still a good day to get outside.
Okay,
Yeah.
and thanks for the opportunity. I'm gonna present there's a cosmic summit that's gonna be, I guess, north, where is it, Greensboro? So this is my part of my preparation.
Good. Glad we can help you.
Thank you.
Okay, everyone. I think that'll be enough for today.
Okay,
Stay
well,
well, everyone.
thank you. Thank you.
Bye.
Goodbye.